Good morning everyone, welcome to our SAF online training series where we will be giving you information on sample preparation and analysis by ICP, XRF and CHNS. Before we start, I would like to introduce the rest of my team. So in charge of XRF and mineral separation is Mareli. In charge of solutions analysis and CHNS is Charney, and our sample preparation technician is Rossouw. So before we get to sample processing, we have to discuss some basic criteria for the very important first step of sampling, since errors here can completely void all the care taken towards good laboratory practice during our sample prep and analysis. So you have your project title, you know what sample material you're going to be working with, example seawater or soil or biological material, and you know what your target analytes are going to be. For example, you're looking at alkalis in soil or trace metals in seawater. The next step is going to be to start sampling, eventually processing your samples, and select the appropriate analytical technique for your sample type and analytes you are interested in. So your choice of analytical technique is firstly determined by whether you have solid or liquid samples. So for any liquid samples, major and trace elements are done by ICP AES or ICP MS, following specific sample processing steps, whether you require total extractable or soluble content of the sample. For solid samples on which you require CHNS, your choice is then only CHNS. Mostly on dry samples where the sample is combusted for analysis. For other major, minor and trace elements, there's different options whether you have inorganic or organic samples. So for major oxide analysis on inorganic samples, your typical analytical technique will be XRF. If you want to measure traces on inorganic samples, it will also depend on whether you need to do bulk or in situ traces. For bulk traces, depending on the amount of sample you have, you will either do XRF analysis when you have more than 8 grams of sample, or you can do laser ablation ICP after fusion of the sample. When you need to do in situ trace elements, in other words the sample features remain intact, your choice will be laser ablation ICP. Both organic and inorganic solid samples can also be analyzed by ICP after digestion for only the total extractable content, not the total element content. The most important is representative sampling. The portion that you sample must represent the whole of your sample material, either by sample size or you have to take a number of replicates. So your sample material determines to a large extent the size and volume that you sample. The more heterogeneous your sample material is over a larger scale, the bigger the sample portion is that you need to sample. So for instance, if you are looking at trace elements in open ocean seawater, you don't need to take a ton of sample material. It's going to be homogeneous over a fairly small scale, so that a half a liter to a liter of sample is going to be representative enough of your seawater. While if you are looking at the whole rock chemistry of some stratigraphic layer or a granite intrusion, you have to take a much bigger sample because grain sizes are much different in this sample. You could have some minerals a couple of centimeters big compared to a few microns of other minerals. So if you only take a fistful of sample, you're not going to be having a representative sample of the whole material. When you're working with very small samples, for instance, if you're looking at flower nectar, where you can typically not sample more than 20 microliters per flower almost, you have to collect several replicates and add them together to have enough sample to work with. Also very important is your sampling media, which refers to firstly your sampling tools. You have to choose your tools for sampling to minimize any contamination. For instance, if you are looking at beach sand for trace metals, you'll be sampling with a plastic scoop and not a steel spade. If you are looking at plant leaves for surface contaminants, you have to make sure that you wear gloves and not use your bare hands. The sample containers that you store your samples in must also contribute minimal contamination, and it must be safe for storage. So you never place any of your samples in glass because of a huge number of contaminants, and it's unsafe to transport your samples as it can easily break. When choosing your sample container, you also have to consider how the sample is going to be extracted for sample preparation and analysis. For instance, you might sample a blood sample of some animal into a glass needle, but to get the blood out of the glass needle is not so easy. An alternative would be to rather store it in small 1.5 ml epi tubes, as it's easy to pipette it for further processing. You also have to consider sample stability. Any liquid samples you might need to acidify or freeze to prevent any fungal growth, and other samples that can spoil, first freeze them before you process them further. Then last but not least is communication. You need to contact the analytical lab before you start any sample preparation. Confirm that your preparation method is going to be suitable for analysis if you are going to be doing the sample prep yourself. For example, digestion of river water for trace metals and mercury should never be done in open glass vials, as there could be volatile loss, for instance your mercury or lead, and not on a hot plate using AR grade acids, because there's a huge contribution of contamination from the acids. Once you've contaminated your samples, nothing can be done afterwards. You cannot take the contaminants out. It's not ideal to subtract blanks, so make sure you do not add any contaminants during the sample processing.
The laboratory can test various sample types for CHNS analysis. These include high-density oils and dry solids that mold into particle size of less than 100 micron. These solid samples vary from soils, plants to synthetic chemical products. Sample size for the analysis ranges from 5 to 50 milligram, depending on sample type and composition. However, we can analyze and quantify on a minimum of 1 milligram synthetic sample, since the composition is generally greater than 10%. The image shows a 10-gram chunk of coal. This sample is then molded into a size fraction of less than 100 microns. This illustrates the importance of providing a homogeneous sample, as only 10 milligram of this will be analyzed and quantified. The finely molded samples are weighed into the aluminium sample boat using a 4-decimal analytical balance. Approximately 5 milligram tungsten trioxide granules are added to each boat. This additive protects the glass tube against the vigorous reaction during the combustion process of the sample. The sample boat is then carefully folded into a small ball. If any of the sample is lost during this folding process, discard sample and start over. It is crucial to the analysis that the sample weight is recorded accurately, as the method is dependent on the sample mass analyzed. Here we have a few examples of samples routinely analyzed by the CHNS Vario EL-Cube elemental analyzer. As mentioned previously, we can analyze a wide range of solid samples provided that they are dry and homogeneous. It's important to note the image of the oils. Sample viscosity should be as the oil on the left in order for us to successfully quantify the CHNS in the sample. There are certain sample types that can pose a problem when either preparing or analyzing the sample. If the sample contains any amount of fluoride, the laboratory will not be able to analyze it. Fluoride has a severe damaging effect on the adsorption column of the instrument. If a sample has residual moisture in it, the sample will not be analyzed. The result is dependent on the mass of the sample weighed, and if the weight of the moisture is included, the result will be skewed. Liquid samples cannot be analyzed due to the high risk of the sample leaking out of the boat. Samples containing salts will be evaluated, as high salt content can damage the tubes. It is therefore crucial that all available information about your samples are given to the lab to ensure proper sample handling and preparation for accurate data.
So let's look at sample preparation for ICP analysis. So what can be measured by ICP? Almost all of the elements on the periodic table can be analyzed, but they need to be extracted from samples and be presented in a solution form. So if you take a leaf sample, it first needs to be milled and powdered and then microwave digested to present it into a solution form for analysis. There are different ways to get from your solid sample to a solution, so the purpose of your study is crucial to select the appropriate sample processing. Many different sample types are processed and analyzed by ICP AES and ICP MS. These samples can be either organic and inorganic, solids as well as liquids, and they can be generally classified in a number of groups. For instance, we've got clinical and biological samples such as blood or organs, food, sludges and oils. These samples require complete digestion to analyze its elemental content. When you are looking at vegetation samples, you want to digest them for the total extractable content, even though there sometimes might be some insoluble components present. If the purpose of your study is to look at surface contamination, you might not need to completely digest the samples. They might just be rinsed in an appropriate solution to extract the contaminants from the surface. For soils and sediments, you might either be looking at the extractable content or the total element content. For the extractable content, this can be obtained through various different ways, either by different extraction solutions or by microwave digestion. For the total element content of soils and sediments, this typically requires a 4-step acid digestion to completely break down all of the silicate minerals. This is not done at SAF, as it requires HF acid to be used. An alternative for ICP analysis, if you're looking at total element content in soils and sediments, was to use XRF and laser ablation traces. Though there are some limitations, you won't be able to analyze all of the elements such as the volatiles that could be lost in the sample processing step. Beverage samples for ICP analysis could be either digested or diluted. It will depend on the type of sample. Where you have water samples, it could be digested for total content if there is some turbidity in the samples, or it could just be acidified for the dissolved content. So when looking at the preparation of all these various sample types to get them into a solution ready for ICP analysis, we will split them into processes for solid samples and processes for liquid samples. And here's just a summary schematic of the different steps that could be involved in the sample processing. So solid samples could either be directly digested instead of undergoing any treatment like drying, sieving or grinding. This could be, for instance, if you have a biological material such as homogenized liver, it's going to be wet digested, so it doesn't need to undergo any of the different steps. You can have most of the environmental or biological samples typically would need drying, grinding and then digestion. You can have soils that will have a sieving step in between, but all of the different steps would be determined by the purpose of the study. If you look at liquid samples, they could be digested immediately if they do have some turbid material. They could be filtered and then just simply analyzed. They could be acidified before analysis or diluted if it contains any high volumes of salt that will interfere with the ICP measurement. So let's look at all of these different processes in more detail. So looking at solid samples, most samples will require a drying step first before they can be homogenized and grind into a small enough mass for digestion. Because if you look, for instance, at mussels that are sampled for trace metal analysis, you'll end up sampling maybe 10 or 20 mussels where they each weigh about 5 grams per mussel, and eventually we only use 0.5 gram for digestion. So you can see if you would have only sectioned 0.5 gram from the wet mussels, you might not really have a representative sample of your set of mussel materials. So you will need to dry them, grind them into a powder, and only from the dried powder you'll select your 0.5 gram for sampling and digestion. Again, going back to the initial requirement for sampling, what you ultimately analyze must represent the whole of your sample matrix. It is also important when you start off with wet samples that you record the wet weight before and after drying so that you can recalculate the results back to a wet weight of sample. The most preferred way of drying your samples would be to freeze dry it, or alternatively oven heating, but not above 60 degrees, otherwise you might end up losing some of the volatile elements. This is not typical. Some solid samples might require sieving before preparation in order to remove organic material or large pieces of rock from the sample. Also, if a specific size fraction is to be selected for further processing. When trace metals are of interest in this analysis, it's best to avoid metal sieves and rather use something like a nylon sieve. Most solid samples will undergo a grinding or milling step to reduce the coarse fraction, which could typically be around 500 microns, down to a very fine fraction of less than 100 microns, in order to ensure a homogeneous sample material from which we will eventually take 0.1 to 0.5 gram of sample for digestion. Various grinding vessels can be used, but they may or may not contribute some trace metals in the process. So when you use tungsten carbide mill pots, they will contribute large amounts of tungsten, carbon and cobalt, as well as trace amounts of tantalum, titanium and niobium. This is mostly only used for geological sample material. If you use a stainless steel grinding mill, you could contaminate iron, chromium and nickel. For soils, it's best to use agate ball mills or agate mortar and pestle for plant samples, anything that requires milling without contamination of trace elements. Once you have prepared your samples to the right size fraction according to the purpose of your study, the analytes of interest can now be either extracted with dilute alkaline or acidic solutions. For examples, in soils, ammonium acetate is used for exchangeable cations, and you've got a Melig-3 solution for plant available phosphorus. Alternatively, the samples are digested using hot plate or microwave digestion. Again, the type of digestion method you select also depends on the purpose of your study. They have advantages and disadvantages. For instance, hot plate digestion is usually cheap process, doesn't use expensive equipment, simply a hot water bath and some glass tubes. The disadvantage is those glass tubes are a source of contamination. You can also have evaporation of volatiles as it's an open vessel digestion. Compared to microwave, it's very fast, so in less than an hour you can have your samples completely digested. It's closed vessels, so there's minimal loss of volatiles. It's quartz or Teflon vessels, so there's less contamination. Disadvantages are that it's expensive to buy the equipment. It can be expensive to maintain the digestion vessels. If you have to work with very small sample masses, such as less than 10 milligram, you can end up having very high dilution factors just because you're adding a lot of acids that needs to be diluted again. The amount of digestion vessels that you have access to limits the throughput, so you can have a carousel that has only 12 digestion vessels, or carousels that's got 30 or 40, which could make the analysis slower or faster. Hot plate digestion is best for dirty samples such as soils or sediments, but also when volatile elements such as lead or mercury is not important. Microwave digestion is preferred for most samples, specifically where trace element measurement is of importance. A number of acids are available to digest different types of samples, but they all have some advantages and disadvantages, and not all of them are preferable for introduction into the ICP instrument. So the most often used acid, nitric acid and hydrochloric acid. Nitric acid is used for most materials, metals, alloys, biological samples. It's most preferable for ICP-MS work as it does not introduce any interferences into the measurement. Hydrochloric acid is often used with nitric acid. It can increase the temperature of digestion, and it's beneficial when you've got elements such as mercury that you want to keep in solution. In high concentrations, it can generate some interferences into the ICP-MS, so it's not ideal to do digestion only in hydrochloric acid when you've got small sample volumes and you do measurement for trace elements. Hydrofluoric acid is used to dissolve silica-based materials and geological samples. It attacks glass, so you can only use it in microwave digestion, but it's extremely dangerous to work with. It's also not a preferred acid in the ICP measurement because many of the components in the instrument is glass, and we cannot introduce even dilute concentrations of HF acid. You can neutralize HF acid with boric acid, but it's not always very efficient, and we do not want to accept samples that has been digested with HF due to the problem of instrument glassware being damaged. Hydrogen peroxide is a very strong oxidizing agent. It's often used with other acids to digest organic rich material or fatty samples such as fish samples. It's useful in ICP-MS analysis as it does not introduce any additional interferences. Sulfuric acid is sometimes used, but it's an extremely hazardous acid to introduce into any ICP instrument as it deteriorates many of the metal parts of the instrument. It's a very difficult matrix to decompose in the plasma because of its high boiling point and viscosity. So it's preferable not to digest any samples in sulfuric acid. It's important to note that during microwave digestions, not all sample materials will digest completely, such as soil sediments and some plant materials, where you do have a residue that remains because of insoluble silicate components of the samples. With the usual acids of nitric, hydrochloric or peroxide, this method still only is applicable to extractable content of the samples. It's not a complete digestion.
The laboratory only uses microwave digestion and suprapure acids when solid samples are prepared for ICP analysis. The following acid combinations are used for the effective digestions of different sample types: 6.5 mol nitric acid and 0.5 mol hydrochloric acid when digesting plants and non-fatty biological samples, 6 mol nitric acid and 1 mol hydrogen peroxide for fatty meats and seafoods, and 6 mol nitric acid and 2 mol hydrochloric acid for sediments and soils. When you do your own sample preparation, it is important to include at least one blank and a certified reference material with each carousel. This is used to evaluate any possible contaminants that might have been introduced during your digestion process, and the CRM is used to evaluate the effectiveness of your digestion process. Various certified reference materials are available for different sample types. It is also crucial that you evaluate this prior to starting with the digestion of your samples, as you do not want to discover there was a problem with your preparation after digesting, let's say, over 100 samples. Here we have an example of the digestion process on an organic-based sample. Approximately 0.5 grams of the sample is weighed directly into the Teflon digestion vessel. 6 milliliter of ultra-pure nitric acid and 1 milliliter of hydrogen peroxide is then added to each vessel. Samples are digested in a 12-place carousel where a blank and certified reference material is digested along with the samples. Samples are closed with a Teflon cap and left to pre-digest for 30 minutes. Each vessel is inserted into individual heat protective sleeves before placing it into the carousel. The carousel is inserted into the Mars microwave digester. with the sensors to measure the temperature and pressure inside the cavity. The samples are digested according to preset EPA digestion methods. Once the program for the digestion is completed, the carousel is let out to cool before removing the vessels from the carousel. This is to ensure that volatile elements like mercury is not lost during this process. Once the samples are cooled, they are decanted into 50 ml acid-cleaned containers and made up to a final volume, which is usually 50 milliliters. The mass of the sample weighed and the final volume are what is used to calculate the result that will be produced by the ICP back to the original concentration in the sample, expressed in microgram per kilogram or milligram per kilogram.
For the processing of liquid samples for ICP measurement, the sample treatment is determined by the study objectives. Are you looking at dissolved content or total content of elements in your samples? So when the dissolved element content is of interest, which mostly applies to river, borehole or seawater, you treat the samples differently whether they are clear or are turbid and containing some particulates. So if the samples are clear, you simply acidify it to a pH less than 2 with superpure nitric acid and add some hydrochloric acid for mercury, and the sample can then be analyzed. If the sample do contain some particulates, you either filter or centrifuge the sample. Different filter sizes can be used, 0.45 micron if you only want to remove particulates, 0.22 micron if you want to remove bacteria or viruses or ultrafine particles. The sample can also be centrifuged. That doesn't introduce any additional sources of contamination. Then after filtration or centrifuging your sample, it's again acidified and ready for analysis. If the total element content is to be measured, which would apply to water samples, any beverages or viscous liquids, you cannot filter the sample. It either has to be analyzed directly or digested. If the sample is clear and it doesn't contain any particulates, you can simply dilute or acidify the sample and then analyze. If the samples do contain any particulates, it needs to be digested first using nitric or nitric and hydrochloric acid before the sample can be analyzed. When you want to send your collected or prepared sample to the lab for analysis, it's important that you choose the right type of container so that you don't introduce any contamination, that your samples are safe to transport, and that it's easy for us to extract the sample for any processing that we need to do. So plastic containers are always preferred above glass, as the glass can easily break. Plastic also introduces very little contamination. We prefer samples to be sent in 50 or 15 ml plastic centrifuge tubes, as it easily fits on our autosampler racks. For samples that doesn't require any further processing. When you send samples in bottles, it takes us additional time to pour it out of the bottle into a tube. So best to just send it in a 15 or 50 ml centrifuge tube already. When you have samples that we need to extract again for either CHNS or ICP analysis, make sure that it does not stick to the bottom of the sample tube and it's virtually impossible for us to extract the sample without adding some contamination during the extraction process. Rather use smaller epi tubes for small sample volume so that we can easily pipette the sample out again for further processing. When you extract blood samples, for instance, it's extremely difficult to get a blood sample out of a glass syringe into a digestion tube. It's firstly dangerous because it's difficult to correctly break the glass tube, and often a lot of the sample still sticks to the glass tube and cannot be efficiently extracted for processing by either digestion or dilution.
XRF analysis can be used to analyze a variety of samples from solids to liquids. At our XRF lab, we focus on the analysis of solid samples since ICP solutions are available for liquid samples. Solid samples include, but are not limited to, glass, cement, soils and sludges, raw materials such as sand, limestone and dolomite, and refractory slags. XRF analysis is ideal for most rock types to perform complete whole rock analysis of major and trace elements. The aim of the sample preparation in XRF is to prepare a sample that is homogeneous, has a flat analytical surface, and that will fit into the sample cup holder of the XRF spectrometer. The preparation of samples for XRF analysis can be done by two methods. The first is by making a fusion disk from your sample or a pressed powder pellet. The decision as to which method to follow will depend on the elements to be analyzed and the estimated concentration thereof. To make either a fused disk or a pressed powder pellet, the sample needs to be in a fine powder form. If it is not in a powder form, it will have to be crushed, milled and dried, as would be the case with rock samples. A description of each step will be discussed as set out in the display diagram. It is important to note that the main objective of the two methods is to reduce the particle size and homogenize the sample, all in the attempt to reduce mineralogical effect. The term mineralogical effect will be discussed in more detail in the XRF course. To discuss the crushing and milling methods, we will look at a rock sample as an example. Of course, these procedures may differ depending on the sample type, as a different approach may be needed for other materials. During field work, a bulk sample will be collected from the outcrop. Selected fresh rock pieces, meaning unweathered pieces, are placed in a jaw crusher to crush the sample between 1 to 2 cm rock chips. A rigorous cleaning method of the crusher is done before and after crushing to avoid any contamination. The jaw crusher works well for rather large sample volumes of about 1 to 2 kilograms. Smaller samples can be broken down into pieces by a hand crush or hammer. Using a swing mill, the next step is to grind the sample into a fine powder of less than 80 microns. Most mill pots can only take a handful of chips, so the sample will need to be subdivided into smaller fractions. Overloading the mill pot can lead to a powder that is too coarse. The sample can be divided by various methods, such as the cone and quarter method, or by using a riffle splitter. The riffle splitter is very easy to use, but is hard to clean and can be time-consuming, and can potentially introduce cross-contamination. The cone and quarter method is the preferred method in our lab. These methods are used to ensure that your fraction sample is still representative of the 1 to 2 kilogram bulk sample, as heterogeneity can be very apparent in some sample types. Similar to the jaw crusher, the mold pot also undergoes a rigorous cleaning procedure before and after milling of the sample to avoid any contamination. Mold pots are made from different material such as tungsten carbide, chrome steel, carbon steel or ceramic. The choice of mold pot can introduce certain contaminants. It is very important to know what type of mold pot is being used during the preparation. Always inquire about this, especially when sending samples away to a lab for preparation. To make a good decision to minimize contamination, it is important to establish what are the elements of interest and their expected concentration levels. The table displayed provides an indication of the contamination in parts per million during certain time intervals. Needless to say, the longer the milling time, the higher the contamination, but the finer the sample will be. Optimal milling time is thus of critical importance. Our standard procedure allows for 2 minutes of milling to obtain an optimal powder, but it can vary depending on the sample. If only major elements are being determined, contamination during the grinding process will normally not be a problem. For rock and soil samples, the ideal mold pot is a tungsten carbide, which will add tungsten and cobalt as contaminants. Once an optimal powdered sample is achieved, the sample is dried at 30 to 40 degrees Celsius to remove any moisture. After the sample is dried, the fusion process can begin. Loss on ignition or gain on ignition is determined by igniting the sample at 1000 degrees Celsius in a muffle furnace. The sample is weighed out and mixed with a flux suitable to the sample type and elements of interest. The mixture is melted and turned into a homogeneous glass bead. The purpose of adding a flux to the sample is to lower the fusion temperature of the sample and allow it to melt. An optimal sample to flux ratio must be achieved for sufficient melting to occur. A common ratio is a 10 times dilution, for example 0.7 grams sample to 7 grams of flux. The ratio can be adjusted depending on the sample type and flux composition. The fusion method is ideal for major oxide analysis as it removes particle size and mineralogical effects. Fluxes are usually made of lithium borate mixes and are classified in their ability to react with either a more acid sample or basic sample. Acid samples are high in silica, aluminium, iron or sulfur oxide, whereas basic samples are high in calcium, magnesium, potassium and sodium oxides. The choice of flux will thus depend on your sample type. The fluxes are often in a powder or granular form and range in purity. Additives can improve flux performance in the dissolution of certain crystal structures and lowering the melting point. A releasing agent is also added to the flux mixture to aid in the releasing of fused bead from the mold. Once the correct flux is selected, an optimal sample to flux ratio is determined. The weighed sample and flux is placed in a platinum crucible. The crucible and its content is heated at a temperature between 800 and 1000 degrees Celsius. The temperature may need to be adjusted according to the sample type. It is very apparent in this fusion process that pre-knowledge of the sample type is extremely important to allow for correct selection of flux, sample flux ratio, and fusion temperature. Once the mixture is melted, it is casted into a mold and cooled down to form a fused glass bead. Some samples containing reduced species may react with the platinum wear that can seriously damage the platinum crucibles and molds. Since the platinum wear is very expensive, this should be avoided at all times and great care must be taken. The quality of the platinum ware will also influence the success of the fusion making process. Pre-oxidation is essential if samples contain reduced species such as organics, metallics, carbides, sulfides, and phosphides, as they do not dissolve in the flux but attack and destroy the platinum crucible. Pre-oxidation can take place outside the platinum crucible by heating the sample to 1000 degrees Celsius in a suitable vessel in a muffle furnace. Consistent and reproducible preparation of fused beads is not easy and is a science on itself. It takes adequate knowledge and experience in all aspects of the process to deliver good quality fusions. The analysis will only be good as the fusion. Lacking this expertise may allow for problems to occur, such as non-filling the mold, cracking or crystallization, bubbles in the fused bead, bead sticking to the mold, and inhomogeneous dissolution. The aim is to create a good fusion which is perfectly flat and completely homogeneous. A pressed powder pellet is ideally used to analyze trace elements, as the dilution ratio of flux to sample in a fused bead may be too large, or to avoid the loss of certain volatile elements during the pre-oxidation or fusion process. The first step in making pellets is to mix the dried sample powder with a binding agent. A wide variety of additives are available, but most commonly used is mauve oil or a type of wax. The binder acts as a type of glue to hold the powdered sample together in a shape. The binding agent must be contaminant free, binder to the sample ratio should be low as possible, and the sample and binder must be mixed well. Around 5 to 8 grams of sample is required to form a sufficient pellet. The mixture is pressed into a pellet by using a stainless steel press. The pressed powder pellets are dried at 50 degrees Celsius to avoid any absorption of moisture until they are ready for analysis. After the preparation of either fused bead or pressed powder pellet, analysis can occur. The disc or pellet is placed inside the sample cup, which in return is placed into the XRF spectrometer for analysis. With correct storage conditions, fused beads and pressed powder pellets can be used multiple times. It is thus a non-destructive technique. In addition to XRF trace analysis on pressed powder pellets, the fused beads used for major element analysis can be reused for laser ablation ICP trace element analysis. After the XRF analysis is completed, the fused bead is crushed into small chips. These chips are carefully selected and molded into an epoxy mount. The mount is then placed in a secure sample holder to perform the laser ablation. From everyone at the ICP and XRF unit, we would like to thank you for your time. We hope you enjoyed the session and gained additional knowledge as to how to properly approach your sample preparation and what all the different techniques entitle for each analytical method. The first and most important step to good results is in your hands, so please help us in providing well-prepared samples for analytical work. If you have any questions, you are welcome to contact our team for guidance. For more information on Central Analytical Facilities, please visit the SAF website and like the Facebook page. For weekly info on our ICP and XRF unit, please check out the LinkedIn page. We wish you all the best for the work ahead.